Hi, in this video, we will see how we could design a state feedback controller with integral action for a DC motor. So the outline of this video as follows. We have a physical system which is DC motor. We will build a mathematical model of the system based on the differential equation. And then from the differential equation, we will derive the state space of the DC motor. And then we will design a state feedback controller based on two strategies, volt placement and linear quadratic regulator, LQR, and then we will simulate the whole system in the MATLAB. Now, DC motor convert the electrical energy into a mechanical energy. It's used the permanent magnet type and the armature winding. When the motor accelerates, it generates a voltage. This voltage will be opposite to the input voltage to the motor. Now, the electrical equivalent circuit for the motor is consist of resistance and inductance. So the two elements are the equivalent electrical circuit. Now, for the rotary part, for the shaft, so the free body diagram has inertia, moment of inertia, and also has a damping factor. Now, the input to the system is the voltage. So the voltage is the input to the system, and the output that we are consider in this video is the rotational speed of the shaft, omega. Now, in order to derive the differential equation of the system, we need to understand the physics behind the electrical part and the mechanical rotating part of the DC motor. Now, we will use the voltage. We will use the voltage to build the differential equation. So we need to know for the electrical part how the voltage are calculated in the resistance and in the inductance. So the voltage in the resistance is the resistance multiplied by the current I, and the voltage in the inductance is the inductance multiplied by the derivative of the current I. Now, in the term of the mechanical rotating part, we have two elements, which is the inertia and the damper, and we need to know how to calculate the torque in each element. So in the inertia, the torque is the moment of inertia multiplied by the rotating accelerator, which is the omega dot, and the torque in the damping is the damping coefficient multiplied by the rotating of the shaft, the rotational speed. So this what we need in order to build the differential equation of the DC motor. So for the electrical part, we will use the Kirchhoff voltage law, which is the summation of voltage equal to 0. So we have the voltage source minus the voltage across the resistance minus the voltage across the inductance minus the voltage that generate from the DC motor as an opposite voltage. So we already know all these three terms. We have just a problem with this term. So this term is related to the omega, which is the rotational of the shaft, and Ke is the coefficient. So by substituting this formula in this equation, we have the final equation, which is the voltage minus the voltage across the resistance, the voltage across the inductance, the voltage that generated from the rotating of the shaft. For the mechanical part, we will apply the Newton's second law, which is the summation of torque equal to 0. So the torque that's supplied to the system that comes from the motor equal to the moment of inertia, or the torque in the inertia, and the torque that generated from the damping. Now, this torque is related to the current that applied to the motor. So the formula for this torque is the coefficient Kt multiplied by the current. So if we substitute this formula, we will get Kt multiplied by the I, which is the torque supplied to the mechanical part, and the two other terms. So this is the two equations that we need in order to derive the state space model of the system. Now, in order to build the state space model, we need to rearrange these two equations to suit the purpose that we need to build the state space. Now, because we know that in the state space there is the relationship between the derivative of state and the state, so we need to take the derivative of I in this term, and we take all the remaining in other side, and we divide it by L, because we have the coefficient L with the derivative of I, the current, and we do the same thing here because we have the derivative of omega. So we take the derivative of omega on this side, and with the remaining on other side and divided by the moment of inertia J. So we will have these two formulas that we will use in order to build the state space. So based on these two equations, and we already know the state space, the formula of the two equations of the state space, we will start building our state space. Now the two state in our system is the current, we will name it as x1, and the rotational speed omega, and we will name it x2. And the input to the system, which is the U, is the voltage. So now we take the first one, which is x dot. So we have like x1 and x2, the current and the omega. So here is the x1 dot, x2 dot, so the derivative of the state. And A is the matrix represent the relationship between the derivative of state and the state itself, which is x1, x2. So in terms of the first term, which is x1, the current, so the derivative of current, what's the relationship between the derivative of current and the current? So if we go to this formula, this equation, this is the derivative of current and this is the current. So the coefficient is minus R divided by L. So we will put this term. Now, what's the relationship between the derivative of current and the omega? So this is omega and this is the derivative of current. So minus Ke over L. Now, the derivative of omega, what's the relationship between the derivative of omega and x1, which is the current? So this is the derivative of omega and this is the current. So we have Kt over J. And what's the relationship between the derivative of omega and omega, which is minus B over J. So this is the matrix A represent the relationship between x dot and x. The same thing we will do with the input, which is the voltage. What's the relationship between the x1 dot, which is the current, with the voltage? We could see that 1 over L. And if we look to the derivative of omega, there is no any voltage, so we put 0. Now the question now, what's our output? So the C represents the output matrix. Which of these two states we are interested? We are interested to control the rotational speed of the motor. So from these two states, we don't interest in the current, so we put 0. And we put 1 for the rotational because we are controlling the speed of the motor. Now, based on these two equations, we could have this, the final formula of A and B and C and D. And this is what we will use in the MATLAB to build the model. Now, if you want to have more information, I will put a link to explain more about the state space modeling. Now, after we get the state space modeling, we will go to design the controller. Now, we know in the control system, we have two problems, the regulator and the tracking. So in the regulator, the problem is to guarantee the stability of the system and also to improve the transient response, the shape of the transient response. So for example, we don't need oscillation in the system. The settling time, we need it minimum as we can. Now, for this job, we have the pole placement and the LQR. These two techniques work on the transient in order to guarantee the stability of the system and shape the response. However, these two techniques, they don't solve the other problem, which is the tracking problem, to remove the steady state error. And there are two ways to remove the error of steady state. In the previous video, we used the DC gain. In this video, we will add the integral action to the state feedback controller in order to make our system follow the zero steady state. So follow a reference with a zero steady state. So again, if you are interested to understand the feedback control with integral action, for more information, I will put a link explain this in step by step. I will assume you already have a knowledge about this, so I will just quick explain the point. Now, this is the structure of the system with the feedback controller and integral action. So this is the integral action. Now we have a new state to our system. So in order to build our state space model of the system, we need to consider this a new state. So this is the new state. This comes from the R minus L, minus Y, sorry. So R minus Y. And Y came from the X multiplied by C because D is 0. So if we have this formula for X dot, now X for the E dot, now we already have X dot. We just added a new derivative, a new state with the derivative of state. So now, what's the relationship between X dot and X is the same A as before, this one, A. Now, what's the relationship between X dot and E. So X dot and E. So if you go here, there's no any E, so we put 0. Now, what's the relationship between E and X? So this is E dot and X, so this is X, so minus C, so we put minus C. Well, the relationship between E dot and E, there's no E in the equation of E dot, so we put 0. So this is the new A after we put the integral action. The same thing we will do with the B. So this is the B, so X dot, the relationship between X dot and U is B, and here there is no U, so we put 0. But now we have a new term, which is R. So what's the relationship between X dot and R? There is no any relationship, so we put 0 with the name, with the same number of state we have. So for example, for our DC motor, we have 2 states, so we have 2 0 here. Now what's the relationship between E dot and R? It's 1, so we put 1. So this is the new formula of our system. So we have like XE, so which mean we have another state, which is E dot. So this is the new X, just to separate X from X sub E. So this is the new, which is become 3 state now in our system. And this is the new A, the new state BU, BR multiplied by the reference. Now again, we will select the control law as R minus K, which is, this is the feedback, this K and this 2K, because we have 2 state here and we have 1 state here, so we have 3 state now. So to understand, this is Kx have 2 state and this is Ke have 1 state, multiplied by the new state of our system. So this is the current and the rotational speed, and this is the new E that comes from the integral action. Now, by adding this to our equation, we will finally end up with these two, A closed loop and B closed loop. So A closed loop is AE, which is already this one, multiplied by the K, which is 3 terms, vector with the 3 values, and BE, which is the new our B. And also we have the B closed loop, which is the summation of the BE with the BR. We have BE and BR. Now, in order to determine the K, we will use the two strategy, which is the pole placement and LQR. Now, the idea of the pole placement, that we have the location of the open loop pole of the system. Now, by having the pole placement strategy, we could move this pole to a new desired location of our system. Now, by selecting the best K, which is the feedback K, we could change our location of our pole. So this is the basic idea of pole placement. And I will put link in the description for more description about pole placement. For the linear quadratic, it's different strategy. Linear quadratic use this index in order to generate the optimal U that submitted to the system in order to improve the performance of the system. Now, as compared to the pole placement, so the strategy of pole placement is to select the location of the pole, and then we generate the feedback gain matrix K. But for the LQR, we have two adjustment matrix, which is a Q and R. These two matrix, you have like a trade-off. You have like a trade-off in the design between what you want. You want a response, fast response or a slow response. So if you have, if your requirement is your response to become very fast, very good, so you have to put in your mind you need a large control input. In some application, this is not applicable. You can't use like control action like too much because of the system, because of your actuator. So in order to control the control action, the energy that will be consumed by the control action, we have the matrix R, which is penalize how much you put on the control law. So if you put R large, so you are saying to your system that don't use control action too much. But if you increase Q, you tell your system that I am interested to have a good response. I don't care about my control law. So it's up to you as your designer how you play with the Q and R for your system. Now let's go to the MATLAB to simulate the system with this value of our motor. So we have the moment of inertia, we have the damping, we have the KE and KT, which is the two coefficient of the DC motor, and we have the resistance and the inductance. By having this value, let's go to the MATLAB and see how we could simulate our system with the integral action. Now we will start with the pole placement. So in the beginning, we have the CLC to clear the window, clear all, close all. So clear all to remove all the value of your in the workspace, close all to close all the window in the system. This is the DC motor, so we use it from this table. So based on this table, like the JBKE, so we put this value. So this is the value of the DC motor. Now this is the open loop state space of the DC motor. So if you go back here, so this is the A matrix BCD. So we use this matrix here to build the open loop state space of the model. Then we are simulating the open loop. So if we run the code up to this point, so this is the open loop response of the system. So as you can see, the system has error steady state, and also like you maybe you want to improve the transient response of your system. So the first thing that we will do to our system is to integrate it with the control action. So if you go to the last slide, this one, so we need to build this new matrix, like the new A, the new B, with the integral action. So as you can see, the new A is the same A with added the C and this 2 0. So here you could see, so the new A with the integral action is the A and 2 0 and C and 0. So this is the A with the integral action. This is the BI, so the B with the integral action. So if you go here, so this is the B with the 0, with additional 0. So we put the 0, so this is the new B. And the same thing with C, because we are having another state, so we put 0 for the state that comes from the integral. Now we will build our controller based on the pole placement. So as you can see here, now the location of my poles is far away in the negative part in order to improve my system. So if you just run the system up to kx, so you will have now, you will see 3 gain. So this is for the DC motor and this is for the integral. So this 2 for the 2 state, and the last one is for the KE. Now as you can see, this is the gain that will require to apply to the system in order to locate this pole of the system in this location. So if we continue the code, this is the BR. So the BR, if you go here, so the BR is zeros as number of state you have. So we have 2 state and 1 for the integral. So we put 2 0 and 1, and this is the B closed loop. Now if we run the system, so the system with the integral part with the state feedback based on the pole placement. Now if we run the system, now you will see this is the open loop of the system and this is the closed loop. So we remove the error steady state and also we improve the transient response of the system. Now you could have another location. So for example, if I just change the location of the pole, so I put -6, let's say 14, 15 for example, and I run the system, you will see like your response is different now. So it's depend on how you choose the location of the pole of the system. So if I put it so far from the original, so as you can see now, the response is changed to this. So it depends on the designer how you select the location of the pole in order to improve the performance of the system. And as I said, this is the gain. This is for the integral, this is for the current, this is for the rotational speed, and this is for the integral part. Now if we go to the LQR, the code is the same. So this is the parameter of the system, this is the open loop, and this is the response. So if we just simulate the system, so this is the open loop system. Now we will add the integral part. So here we added the integral part. Now the difference now between the pole placement and the LQR is to select the Q. Now I select this value. Why? Because this is like responsible for the current, and this is responsible for the rotational, and this is responsible for the integral part. Now our problem is with the integral part, because this is on the original. So we need to tell the controller that to put too much weight to improve the performance of the integral, because it's closer from the original, and we need to shift this pool far from the original. So that's why we put too much weight on the last one. And this is to tell the controller, I don't care about my control law, it's cheap, I could have any control law. So based on this selection, if you just run the system up to this, now again, you will see your control gain, the feedback gain matrix is so much big. It's too big. But in order to improve the performance of the system. Now, if we run the system, you could see that your response is like the transient response is improved, and also the steady state is removed. But if you change, for example, this, you put it like, you reduce the value and you run the system, you will see like different. So your system becomes so slow. So as you can see, your system, the settling time become 1.8. But if we just increase the weight on the third one, the one that is closer from the original, look, your performance is improved. And if you improve this one, which is the, now your response is still not far. So let's increase this one and this one. So by changing the value of Q, so as you can see here, the difference, your response now, the settling time is 0.25, and the error steady state is removed. So this is all about this video. We explain how we develop the state space of the motor, and then we design a state feedback controller. And we say that there is a problem with the state feedback controller, regardless you use pole placement or LQR, is the error steady state. Now we remove the error steady state by adding the integral part. Thank you.